Welcome to the official start of data mining. I'm now going to share our screen. There we go. And so pulled up on the screen, I have the set of notes for this week. In here, we're going back to doing a bunch of Python stuff. And in particular, we're going to start looking at text data and how you apply all these sort of really theoretical abstract things that we've been working on to text data domains. There'll be, so we have about 3.5-4 weeks left in the semester until Thanksgiving. During that time, we'll be introducing a homework assignment today, and then there'll be 2 more programming homework assignments after that. So 3 more total programming homework assignments, and then no more theoretical homework assignments. So you can use that to sort of judge how much work is left in the course for you. Today, we're going to talk about your next homework assignment and what you need to do for it. And we should finish all of that up today. And then Wednesday, we'll start up on sort of the second homework assignment in this series.
Mike.
Yeah, go ahead.
We didn't have any homework due yesterday, right?
There was no homework due yesterday. Yeah, nothing due last week.
Just wanted to make sure.
Yep. Yeah, you did. Did not forget that. Okay, so today we're going to talk about a technique called transformers, and we're not going to talk in detail about this technique. We're just going to see some of the big picture advantages and limitations of this technique. And in particular, it's going to be a really easy technique to tie into the theoretical stuff that we've been talking about before. And essentially what a transformer is it just somehow, which we'll consider magic, but it somehow converts text into a vector. And there's this library in Python, conveniently called transformers, that does this for us. And so if you were to click right here in the notes, it goes to this transformers library. This library is created by a company called Hugging Face. So up here, huggingface.co is the name of the company. The company, all they do is create open source libraries for doing data mining tasks. And they're particularly famous for their sort of language processing, text processing libraries. The way they make their money is that they then do consulting based on these libraries. So all of these open source libraries are essentially just advertisement for their consulting business. So Transformers is one of their most popular libraries, and what it does is it has about 30 different techniques sort of built in inside of it, which convert a text string into a vector. And the code that we'll be using today, you'll be able to just swap out a single line to use any of these other techniques that you want, and everything else will just seamlessly work. So advantages of this transformers technique: it'll be relatively easy to use, and it actually is currently the state-of-the-art technique for all text classification applications. And when I say all, there's probably some application where it's not state-of-the-art for, but like 99.9% it's state-of-the-art. And the downside, though, that we'll see is that it's extremely resource intensive, both in time and memory. And so this particular homework assignment, you should expect that it'll take somewhere between 5 to 10 hours on your computer to run it in order to get the results for submitting it. On my computer, it took about 7 hours, so I just left it on overnight, and it finished overnight, and that's what I would recommend you do as well. If you've heard of GPUs before, GPUs actually take that 7-hour time frame down just to like 5 minutes or so. So GPUs are a technique for doing, or a piece of hardware for doing matrix multiplications really fast, which speeds up all of these data mining applications. So that's one disadvantage, which is applicable for you all because probably you don't have access to a GPU on your computer. They cost anywhere from like $1,000 to $5,000. But the real one from the data mining perspective is that they get really good classification results, but they provide really bad insight as to why they get good classification results. So starting probably on Wednesday, but definitely by next week, we'll be going over other techniques that actually give you more insight. Okay, so let's see. Before actually getting into what the homework is and some of these other files, I want to start by looking at this example.py. And this is an example of how you use this transformers library to generate vectors, generate feature vectors from text. And so I'm going to switch over my screen to this terminal right here. And on the left, I have a Vim window open to my example.py file. And then the top right over here is just TensorBoard. We're not going to need that right now. And then the bottom right over here, I have the terminal open into the same 09_text folder. And inside here is where that example.py file is. In this example.py file, there's this code up here, which we saw last time is needed just to take away some of the error messages related to using TensorBoard. These are just warnings. They don't really mean anything. So this makes our code, or the output of our code, a little bit more clean. And here I'm importing Torch and this transformers library. And then I have these make features functions right here. And there's two of them, make features and make features batch. And both of these functions I just actually copied and pasted out from the documentation of the transformers library. And so the inside of these functions don't really matter, but what matters is just what they do. We're going to treat them like a black box. And what they do is, scroll down to the bottom of this file. Here, you can see on line 53, I'm calling this make features function, and it's taking as input just this string, and what it outputs is a torch tensor. And so here, features.shape, that's going to tell me what is the shape of this tensor. And then similarly, I'm calling this make features batch function on line 56, and that's also outputting a torch tensor. And I'm going to print out the shape of this tensor. The only difference between the make features and the make features batch function is that make features takes a single string as input, and the make features batch function takes a list of strings as input. And sometimes in machine learning lingo, if you have a set of data points that you're processing at once, they call that a batch of data points. So that's why this function is make features batch, because it's taking in a whole set of data points instead of just a single data point at a time. So over here in the terminal on the right, I'm going to run this code. And up here, we won't get any output from any of this code, but we will get output down here from line 54 and line 60 right here, telling us what is the shape of these features. And this code takes, I don't know, 10 to 20 seconds to run, mostly because just importing these libraries takes a long time. They're big libraries. And there we go. So features.shape gives us a vector as an output, or a matrix where the first column is dimension 1, and then the second column is 512. And so 512 is the total number of features that this make features function is giving us. Why 512? Well, 512, let me type it out right here. 512 equals 2 raised to the 9th power. And it turns out that matrix multiplications and all of these sort of numeric algorithms are much more efficient when the tensors their sizes are powers of 2. And And so that's why 512 was chosen. It would actually, it takes just as much time to multiply a 500 by 500 matrix as it takes to multiply 512 by 512, due to just the way CPUs are implemented. And so people always round up to the nearest power of 2 when they're doing these things. The features batched function returned a tensor now with shape 2 or size 2 in the first column right here, 2 columns, 512 rows. And that's because we had 2 elements of our list being passed into the make features batch function. If we were to add more, another test, a 4th test, then what we would see is that the features batched is going to be 4 here instead of 2. Are there any questions so far about any of this code while this is running?
Yeah, I had a question. Does this library use any of like the sparse, dense matrix stuff that we learned about at the beginning to make computation faster?
That's a great question. So at this point, the transformers library, everything is done using dense matrices. And what I wanted to do next is actually print some of the output of these, just quickly inspect some of these features. So we'll do that, and that'll show us why they use dense matrices. So if instead of doing printing features.shape, if we actually print features like this, what we'll see is that none of these features are not sparse at all. All of these 512 dimensions contain various numbers inside of them. And all of these numbers are going to be within the range of approximately -1 to +1, many of them much smaller. And what is the meaning of each of these numbers? That's a great question that nobody really knows the answer to. It's just a whole bunch of numbers, and somehow these numbers capture various features about this text. And yeah, so you can see that this tensor, no zeros anywhere, so it doesn't make sense to use a sparse tensor to store this. But we'll see actually with the next technique for text that we're going to talk about is the feature dimensions will be really, really large, on the order of millions to billions, and those feature dimensions will use the sparse techniques that we talked about earlier in the course.
People ever tried to remove like parts of these matrices and then like do tests on them to see like what messes it up the most, to try and like figure out some concept of like what's important?
Yeah, this is a great question. So I'll get to that question in probably about 5 minutes though, so hold that thought. I wanted to look a little bit more at this features vector, just one more quick experiment of, instead of printing the entire features vector, I want to print just the first 10 values of it. And we're going to actually do make features. This is a test. So I'm calling make features right here, passing in this is a test, and getting just the first 10 values. And I want to print that 3 times like this. And then what I want to do is make features of this sentence is about data mining, and also print the first 10 features of that. And let's actually print those values. And one last sentence of make features. This sentence is about President Trump. and we'll print the first 10 features of each of these. And all I want us to see is that every time you call this make features function, if you pass in the same input string right here, you're going to get the same result back each time. But if you pass in a different sentence, you're going to get different, potentially very different parameters as output. So here, these three make features calls all about this is a test, this is a test, this is a test, and they all have the same output like this. Down here, this sentence is about data mining, and you can see that these values here, they're all the same, and they're all fairly different from these values up here. Again, what they represent, we don't really know, but we can start maybe getting some intuition about what they represent if we compare the output of these three examples to these three examples. Because here, both of these sentences sort of following the same pattern of this sentence is about data mining, and this sentence is about President Trump. And this first column right here has really, really close to the same value for each of these columns. For each of these sentences. So probably somehow this column is related to this pattern of the sentence says this sentence is about. This sentence is a little bit similar because it's saying this is, and it's this value is kind of similar to this value, but it's more different than this value is to this value. We can sort of test this hypothesis, trying to get more information about what this first column might represent by trying another totally different example. Like we'll do make features of President Trump is running for re-election. And so this sentence right here follows a totally different pattern than this sentence up here. Still contains some of the keywords, same keywords as this one, but very different than these ones up here. I guess there's one word in common, which is the copula. And let's take a look at the output of those features, and we'll see if this first column is a little bit similar or not similar. You'll notice that, so each time, so it takes, 10 seconds before these values start printing at all. And then it takes, kind of half a second between each time one of these values prints. You might not be able to see that super well in the sort of zoom lag, but it takes about half a second each time you call this make features function. And so that's what I mean by this is a very expensive process computationally. But if you're just doing this once, half a second's not bad at all. But in your homework, the data set that you're going to be working with actually has about 10 million tweets inside of it. And half a second adds up pretty fast on 10 million tweets. So here, this sentence down here, President Trump is running for re-election. We now see that this sort of column or this feature is very different than these. We went from being negative to positive. So something totally different is being captured now. The only real techniques that people have for understanding what these features capture for each of these, or for this make features function, is just by trying examples and seeing sort of what comes out, seeing what things are similar and what things are different in different dimensions. So it's very much a trial and error sort of thing. And yeah, it's nobody knows. It's an open research question if they even do represent anything meaningful. So next I'm going to comment out printing all of these things up here. And actually I want to leave one of these uncommented. And what I want to do is come back up to this line right here where it says load the feature generators. And this feature generator string has, right now I set it to t5-small. That's one of the possible feature generators built into this transformers library. Another one of these feature generators is called Albert. And if I just comment out that line and comment this line, then these functions will load the Albert feature generator, and we'll see that we get some different results. So let's run that. And again, it takes a minute to, or not a minute, but 10 seconds or so to run these. And here, whoops, I actually forgot to save this. So we were getting the same results. Now that I've saved this, we will rerun. What you want to notice right now is that for this t5-small, the output dimension here is 512. But for this Albert model, the output dimension is 768. And so we have, based on our theorems of from the statistical learning theory with VC dimension, when we go from 512 up to 768, if we're using a linear model, that means that our VC dimension has increased by 50%. And so we will need 50% more data in order to have the same generalization error. And so that's one of the things to keep in mind when you're selecting one of these feature generators is what is the output dimension of that feature generator. And we can use our discussions about statistical learning theory to determine whether that's enough data for, or we have enough data for a particular dimension, and based on that, select an appropriate model. The other thing you'll notice is that here, these dimensions 1 and 4, those stay the same. Those are not dependent on the choice of feature generator. It's just the fact that when you call make features, you're always going to get a dimension 1 vector. And when you call the make features batch, you're always going to get the same number of rows as you have elements in your list right here. The next thing that I want to notice is that these values in these features are totally different now. So now we were getting this -0.03 up to 0.413, and totally different values. But again, they're still kind of in this range of between -1 to 1. And because they're in the range of -1 to 1, when we if we were trying to put a bound on the total, the L2 norm of one of these vectors, in our discussion of the stochastic gradient descent section, we saw that if each dimension is in -1 to 1, then the L2 norm is bounded by O of square root of D, where D is the dimension, so D being 768 or 512. And so we can just plug in square root of D, square root of these numbers right here, square root of these numbers right here into our stochastic gradient descent bounds, and use those bounds to determine how much data we need. And here, where the advantage of the stochastic gradient descent bound is it works not just in the binary classification case, but also in the multivariate classification case. And our overall bound that we saw maybe 2 weeks ago now was O of, what was it? Rho square root of, what am I trying to write right now? Square root of k divided by square root of t. And this rho value right here is this value right here. this K value right here is the total number of classes that we have. And so now using these feature generators, our data is linear in the number of classes and linear in the number of dimensions, how much data we need. That's the main sort of consideration from our perspective that we care about from which feature generator we're going to use. First of all, wanting each individual column to be bounded in -1 to 1, which all of these ones in the transformers library are. And then the second is what is the total number of dimensions and picking that appropriately. One last consideration, which is maybe from a, well, let's see, depending on your definition of practical, is either not practical or very practical, but how much runtime it actually takes. But if you're on a GPU, all of these models will take approximately the same runtime. That'll be like 10 milliseconds or so per sample. But on a CPU, on your computer, these models vary dramatically in how much time they take to run. And T5-small is the fastest one to run. And so that's the one that in the homework assignment is the one that we'll be using. Any other, let's see, that's all the things that I wanted to cover about the transformers library by itself. Are there any questions about anything that we talked about?
Yeah, Mike, I had a question regarding sort of the output feature dimension. Mm-hmm. Is there a way to change that output feature dimension, you know, like regardless of changing your feature generator?
Yeah, it's a great question. So the basic answer is no. That the only way to change this output feature dimension is by changing what your feature generator is. And if you go up to this URL right here, there's, I think I have that page open. There's a list of all of the, Zoom is blocking it right now. There we go. There's a list of all of the, not that one, not that one. Here we go. Here's a list of all of the possibilities, and the dimension is whatever it says is the hidden value right here. So 768, 1024, 768. If you wanted to sort of further change that beyond this 768 or 1024, that's where the kernel techniques would come in. And so let's say that you had like a really enormous amount of data, and so you maybe 1024 is not enough dimensions for you. You could go up to say like to 20,000 or something by using a polynomial kernel. Or maybe all of these numbers are still just too much for you. And so then that's where the random projection kernel would come in, where you can reduce the dimensionality down from these numbers to, say, 64 or 32. But that's a great question. These numbers are essentially hard-coded, and there's nothing that you can do about them directly. Any other questions about this transformers model or library?
I had one more quick question about the features and sort of what they mean. Are the features capturing, you know, not only like syntactic information about the sentence, but also semantic, or are they only focusing on like, you know, certain aspects of the character string that we pass in?
Yeah, that's a great question. So each one of these feature generators that is listed right here, they all capture slightly different properties. But one of the things that they're all somehow trying to capture both semantic and syntactic things in the sentence. Yeah, each one of these, let's see, so they're sort of grouped into sections. So there's this like big BERT section. BERT's one of the most famous of these transformers. Each one of these sections, GP2, GPT2, those are both other famous ones. Those three ones right there are probably the three most famous of all of these. Each one of these has a paper about it that describes exactly what the sort of features of the input text that they're trying to capture are. In practice, the way to, let's see, so from sort of a data mining perspective of I just want to get good results and understand things about my data, in practice, what we do is we just try them all and see which one's the best for our application. Yeah, when we see our next technique, we'll see that these models are capturing actually more information than the next technique that we'll talk about. But it's kind of some of the reason that these models are hard to understand is because they're capturing so much information. It's hard to see exactly which information they're making important.
Okay.
And actually, one of the things that I also wanted to point out is that, so right now, this Albert model and this T5 small model, they're really designed specifically for English. This model right here, BERT-based multilingual uncased, is designed to work with any possible language. It supports 104 different languages. And then there are other models specifically like specialized to Chinese or to German or whatever your particular language of choice is. So that's another sort of really important consideration when you're selecting one of these transformer feature generators is which language is important to you. Make sure that you find a model that supports that language. If you're only working on a single language, like just working on English, then a model that's only specialized to English will do better, probably in most cases, than a model like this one that's specialized to many languages. And let's see, when I talk about better for these different feature generators, what the feature generator controls is the training error of your model. The testing error, the generalization error of your model, that's all controlled by the sort of the theorems that we've talked about so far, and in particular, these things that I wrote down here about what is your VC dimension, 512, 768, and what is your number of classes and square root of the number of dimensions. Okay. So with that sort of discussion in hand, we're going to go back to what your actual homework assignment is. And in this homework, what you're going to do is you're going to analyze a bunch of tweets written by members of Congress and official congressional bodies. And there's this repository right here, just Congress tweets on GitHub, that contains, I think since the beginning of 2017, every official or every tweet sent by an official Twitter account for a member of Congress, or that includes both the Senate and House of Representatives, or a lot of, so like the Democratic Party has this sort of umbrella Twitter account, same with the Republican Party, and different sort of caucuses or what do they call them? Subcommittees and committees have their own also Twitter accounts where they post things. So the total number of accounts that this repository tracks is about 1,400 different Twitter accounts because it includes things that are not just for members of Congress. And our goal is going to be to predict, given a particular tweet, which is the member of Congress that was most likely, or which Twitter account was most likely to have tweeted that tweet. And why is this useful? Well, we can use it to say predict if I want to know, like, if I have a sentence, say, of we should invade Iraq. That is my sentence. And I pass it to this model. It'll predict various people, various Twitter accounts are more likely to say that than other Twitter accounts. And that tells us information about whether those members of Congress are likely to agree that we should invade Iraq or disagree that we should invade Iraq. And so you can predict, using models like this, try to predict how members of Congress will react to different policy. There's two sort of data sources for this. This one right here, Congress tweets, that's sort of the direct data source. And then here's another data source that you can download that I've slightly modified, which will make things significantly faster to run if you choose to download this one. The disadvantage is that, well, let's see, so they're both large. This one takes about 1 gigabyte of disk space, but this one takes up about 20 gigabytes of disk space. So this one will be faster. On just an ordinary laptop, it takes about 5 minutes to run the entire assignment, but the disadvantage is it takes up a whole lot more disk space. And then your task, you'll modify this train.py program to output a couple of different accuracy measures, which we'll talk about here in a little bit, which will give us better insight to how your model is performing. And then you'll run the model with this particular set of hyperparameters that I've already picked out for you. I would encourage you to try different hyperparameters, especially if you're able to use this data set with that's much faster to run and experiment with things. But since this data set right here is relatively slow, this is the one that takes like 5 to 10 hours to train on. I wanted to give you the good set of hyperparameters in advance. And then you'll, like your actual submission will be to plot these accuracies in TensorBoard, take a screenshot, and upload that to Sakai as the evidence that you've done this. So we'll look at this train.py file next, and after we look at that, we'll talk about the differences between these two data sets and then exactly what these metrics mean. But before we do that, are there any big picture questions about this assignment? Okay. And then, yeah, important thing, the due date is Sunday. And so again, since it can potentially take a long time to train this assignment, definitely recommend you get started before Sunday and let the training happen overnight. So shooting for trying to get it finished by Friday would be a good goal to have. That way, in case you have some disaster, doesn't work, you still have sort of 2 nights to let it run overnight and before the Sunday deadline. Okay, so actually, before actually looking at the train.py file, I want to look at what the data set looks like. So down here, I have this Congress tweets folder. This is the repository that I was just showing you all. And if we look in the Congress tweets, there's a folder called data. And inside this folder, there are a bunch of JSON files. And JSON is a file format for storing data. It's really popular for, well, it's always used for tweet data. I've never seen tweet data stored in any other format, but it's really popular for other formats as well, or for other data types as well. And the way this data is structured is that each day of the year has a different JSON file. And if we open one of these up, so Congress tweets /data/ we'll do 2019-01-01. Then you'll notice that JSON formats look very similar to Python code. And in fact, the vast majority of JSON files are valid Python code. And so here it looks like a list and then a dictionary. And then each one of these dictionary values corresponds to an individual tweet. So this is like a list of individual tweets. And on any given day, there's about 10,000 or so tweets sent by members of Congress. And the ID is, so every individual tweet is given a unique identifier, a 64-bit number. There it is. Screen name is the Twitter user account of the person who sent the tweet. So this one is Representative Lipinski. User ID is the unique user ID for this person. Then the time that the tweet was sent at. If there's any links inside of the tweet, that goes in this link field. But the most important one for us is this text field right here. And that contains the actual text of the tweet. So here it says, Happy New Year, blah, 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 which makes sense because this was a January 1st file that I'm looking at. And so big picture idea, what we're doing is we're taking this, the text of this tweet and passing it into that transformers library to extract out the some feature dimension, some feature vector. And then we'll use that feature vector with stochastic gradient descent, just like we've done before, to train our prediction model. Yeah, one last maybe sort of interesting side note is here, source, Twitter for iPhone. This is the particular Twitter client that was used to generate this tweet. And this has actually been created a number of controversies in political tweets because actually the vast majority of members of Congress do not write their own tweets. They have their staff members write the tweets for them. And you can actually predict whether a tweet was written by the member of Congress themselves or by a staff member based on the source. So Trump, for example, so he's not congressman, obviously, but president, for a while, he was using an iPhone and his staff members were using Android. And so you could tell exactly which tweets were sent by Trump and which were not based on what the source value of the tweet was if you were looking at the API. But that information is not available in the sort of web Twitter interface. That's why you may have, or it's only like data mining specific researchers who use the API who sort of know that kind of tidbit. But we're only going to be looking at the text value of the tweets. And if we go back now to the, there we go, train.py file, I'll go through a high level of this file, just sort of what's going on next. And this file follows the same format as the train.py file that we're looking at before for stochastic gradient descent. It's like 80% the same with just some minor tweaks. So at the top, still just loading the data sets or having the parameters. This data path right here is going to be sort of the potentially most confusing argument for you. It's the only one that you really have to care about. And what it is whatever you downloaded these data sets to, whichever one you're picking, you make sure that data path is the folder that contains the files. So if I were to run this command like this, let's close this, run this command, and I want to run it on those congressional tweets, it has to be Congress tweets /data. So not a particular JSON file, not Congress tweets by itself, but the folder containing all of the JSON files. If you do that and hit enter, you'll see a whole bunch of output will come out, and then eventually we'll see it start training down below on the right. So yeah, loading the arguments, loading the libraries, that's all the same as before. This line 41 is, there's a library called Simple JSON, which is not built into Python, but it's significantly faster than the JSON library built into Python. So I recommend doing pip3 install Simple JSON in order to get this library, make your code a little bit faster. Importing torch and transformers. This code right here converts between CPU and GPU usage. That's something that we can ignore. This logging code is the same as we looked at or had before. Then the part that starts being different and important is this section down here, where we're actually loading the data set to get into PyTorch. And you don't have to make any modifications to this code right here, but I want to give just a high-level idea of what's going on for you. So this line right here is loading up what the actual class labels are. There's this file, which I'll open up right now. It's called classlabels.json. Classlabels.json, you can see it at the bottom right here. And if you load this, this is a JSON file that contains all the actual Twitter accounts in all of that data JSON files. And next to each Twitter account, it contains how many tweets in the entire data set have been sent by that particular Twitter account. And so that you can see that most accounts have sent on the order of about 1,000 tweets over the past 3 years. Some of them, very small number, only a single data point. Some of them are very, very large. I think the largest one was from some representative I'd never heard of before, but he had like 50,000 tweets that he had sent. That's needed in the training code, so it loads that and puts it into this class labels list right here. Then in PyTorch, when you're loading, or it's possible to create sort of custom data set loaders, and that's what I've done right here. And the important thing to note about this, you can look through the details if you want, but the important thing to note is that the entire data set does not get loaded into memory. It only loads one data point at a time as it's needed to load the data point. And because of that, it uses a constant amount of memory independent of the size of the data set, which is really important when your data set is 20 gigabytes because my laptop doesn't have 20 gigabytes of RAM that it can load all this into. So that's just what this code is doing, making sure that we can get access to the data one data point at a time. Here here's the code that we saw before from the example.py function. We're using the make features batch function instead of the make features function because it turns out that the reason people do things in batches is that the way CPUs are designed, it happens to be significantly more efficient to do things in batches. So if I were to do this using the batch function, I can do this process of going from a text into a vector is sometimes called encoding. I can do this encoding step for 8 data points with a batch in the same time it takes me to do the encoding process for 2 data points using just the make features function. So by using the make features batch, it makes it a little bit more efficient. Next, down here, I'm defining my hypothesis class. And here I've called this hypothesis class factored linear. And what this hypothesis class is it's that technique for handling large amounts of class labels that we saw in the last lecture notes. And what we did was we took the matrix, the W matrix, and we factored it into the product of U times V. And that's what this code right here is doing. This linear model, we saw that about 2 weeks ago now, takes the input feature generator dimensions. So that's the 512, 768, 1024, those really big numbers. And then the other dimension of this matrix is going to be whatever the E parameter is. And in our the sort of example hyperparameters I give you, I recommend setting E to be 32 because that gives, I found, just a good overall performance. And yeah, again, by setting, or what our sample complexity is it's proportional to E when we're using this factorized linear model rather than proportional to K, the total number of classes we have. And since we had 1,400 classes, by setting E equals to 32 instead of 1,400, that gives us a big boost in our generalization accuracy. Yeah, in the overall data set, there's about 10 million, 10 million data points in the data set. And so if we were to use, say, the 512 as our feature dimensions and 1,400 times our classes, that's about equal to, so rounding 512 up to 10 to the third, 1,400 down to 10 to the third, about equal to 1 million, 10 to the sixth. So we have about 10 data points per this sort of complexity measure, the product of the number of classes with the number of feature dimensions. But by reducing that to 32, we get an even better ratio of data points to our complexity measure. Again, this is something that you don't need to worry about implementation-wise, though. Then down here is our training code, and all this code right here is exactly the same as we had before. And down here, right here, is where you'll have to add your calculation of the accuracy at K measure. And so I think the next important thing for us to talk about is what exactly does the accuracy at K measure mean? And before talking about that, are there any questions about anything in the code?
Can you go over again the proportion of the number of data sets with the numbers you just did a little bit earlier? Proportion of data points and
let's see, yeah, so there's approximately 10 million data points in the data set, so 10 million tweets that have been sent. And so that gives us an idea of like how complex our model can potentially be in order to get good generalization error. And the way the two factors that affect that are when we're using the SGD bounds, are the dimensions of the feature vector and the number of classes. And in particular, our error is proportional to the square root of dk divided by m, where d and k are up here, and then m is the number of data points. So here, using these particular values of m, we'll do it up here. M is about, we'll do 10 to the 7th, write it like that, and it's about 10 million. And then D is 512 if we use that T5 small model, and K equals about 1,400. Then we have approximately this number here approximately comes out to 1 divided by 10. There's a constant factor in front of the bound, so that yeah, we can't use this to compute exactly what our generalization error is going to be, but it's good that we have our significantly more data than we have for this D times K complexity measure. But it turns out that using this factored linear model, we can still get better generalization performance, because using this model, the instead of having our generalization error equal that, so that's with the linear model, with the factorized linear model, the generalization error was the square root of d times e over m. And so by making e potentially much smaller than k, we can really improve our generalization error. And in particular, I found that using e of 32, so it's an order of magnitude smaller than k, resulted in better performance. This technique actually tends to work really well when there's sort of kind of clusters in the data somehow. And with Congress members, there's a lot of like natural clustering that happens in the data, that you obviously have Democrats and Republicans, and Democrats are more likely to say certain types of things, and Republicans are more likely to say certain types of things, so they get kind of clustered together. And then you have a lot of geographic clustering, like there's the representatives in California versus the representatives in Virginia. Will be saying very different things because the Californians are talking about wildfires, whereas the Virginians are talking about whatever Virginians talk about. I guess in general, anytime I have a large number of classes where large is something above 10, I have found that using this factored linear model tends to result in better performance. But this is sort of like the theoretical justification about why is that we can guarantee significantly better generalization error. That's a great question. Are there any other questions about these numbers and these bounds and how they're relating to this?
So in this instance, what would be some of the classes? Do you know?
Yeah, so the classes are each of the Twitter accounts. That our goal is to predict like whether it's Marco Rubio or Bernie Sanders or whichever congressperson is written a piece of text. And since we have 1,400 of those different Twitter accounts, that's why there's 1,400 different classes. Great questions. Any other questions so far? Okay, then switch over to this screen right here, and we'll talk about what this accuracy sort of at some number is supposed to mean. And so the first intuition, or the first thing to know, is that the accuracy at 1 is the same accuracy that we've sort of talked about before, or used with binary classification. And that was in particular the 1 minus the 0, 1 error. And that's sort of the only accuracy that makes sense for the binary classification. But in multi-class classification, we can sort of measure how well we do by, like, maybe we didn't get the exact right prediction, but we got really close to the right prediction. So for example, if we were to rank all of the all of the Congress representatives, and by the probability that we think that they sent a tweet, then we would get something like maybe if it's a tweet about like we should have universal healthcare, then maybe Bernie Sanders has a probability of like 0.5 and AOC something like 0.3, and then Marco Rubio something like 0.001, with a whole lot of things in between. And so the tweet in question, we'll say, was, we need universal healthcare. And maybe this tweet was actually sent by AOC, but we're predicting that it was sent by Bernie Sanders. And so in this case, we got the answer wrong because we predicted Bernie Sanders, because that Bernie has the highest probability. But AOC is really close to being the correct answer. It's ranked number 2. And so in some sense, like, this is a much better result than if we were to have an alternative result that looked like Bernie at the top still with, say, still 0.5, but then Marco Rubio right below with 0.3, and then a whole bunch of things, and AOC at the bottom with 0.001. According to the 0-1 loss, or both of these two things are equal because both of these two things are predicting Bernie and they're both wrong. But this one is sort of intuitively much better because the correct classification is ranked really, really high. And this one is much worse because the correct classification is ranked really, really low. And that's what these other accuracy measures give us, is a way to differentiate between these two situations. So what the accuracy at K is formally equal to is, it's 1 if the correct label is in the top K predictions, and 0 otherwise. Let's draw a green line right here separating these out. So with this example up here, let's keep it all on the same screen. Use this area right here. The blue and blue accuracy at 1 would be equal to 0. Accuracy at 2 would be equal to 1. Accuracy at 3 would be equal to 1. And everything in between would also be equal to 1. But then with this red example right here, we would have that the accuracy at 1 still equals to 0. And then now the accuracy at 2 is also equal to 0 because we have the wrong class at position 2. And we would have a whole bunch of zeros. And then finally, at the very last position down here, we would have a 1. Let's see. Before I go on to more examples, are there any questions about anything that I've written so far? Okay. The important property, or one of the important properties for but this will be really important when you're debugging your code, this property, is that if you have the accuracy at I, that is going to be guaranteed to be greater than or equal to the accuracy at j if I is greater than or equal to j. Because if you're farther down in this list, once you hit like a 1 at some spot, then you're guaranteed to be 1 everywhere else down below. And so once, yeah, so we have this property right here. In the assignment, I'm asking you to plot the accuracy at 1, 5, 10, and 100. And what you should see is that you'll get really, really great values, really, really good values for this. So you'll be able to get them almost to 0.5. But really, really bad values for this. And it'll be something like 0.05. So a whole order of magnitude difference between these. And that makes sense because a lot of tweets, especially if it's, say, like a generic tweet like I support the Republican Party, then there's a lot of Republican Congress members who could have sent a tweet like that. And so you're probably not going to be able to predict the exact person who sent it, but you can get a big set of people who might have sent it, and so get really good accuracy here. And in order to actually predict like the really, really accurate things, it'll have to be tweets where they're specifically mentioning like, oh, I'm in California's District 26 and we support whatever. But the fact that it has something specific like their district number or that kind of very detailed information will let you predict with these high accuracies. When you're implementing this in code, so let's come down here to the bottom. All the code will go right down here at the bottom, and I recommend, I have 2 hints for you. The first hint is to use this function torch.topk, which calculates the actual top k values. And so that makes sense that that will be useful in computing this right here. And what you'll apply torch.topk function to is to the output of your hypothesis class. That this output tensor is going to, the shape of output will be something like b comma d, where b is the batch size, which I think I have recommended being equal to 64, and d is the dimensions, which will be 512 if you're using that T5 small model. The other hint is every time you create a tensor, print out its shape and tell yourself what shape it is. So the very first thing that I would start with implementing this is output.shape, print it out, and then call the torch.topk function on output, store its output, or the result of that is something like result equals, and then print out result.shape. Based on that, you'll have some idea of how do I implement this if statement right here, print out the shape of all the pieces for that if statement, and so on. If you do this correctly, I have an example output from TensorBoard. As soon as Zoom lets me click above, right here. This is approximately what your output will look like. So I'm requiring that you go up to at least 10,000 iterations of stochastic gradient descent. You can do more, and the model will continue improving for quite a while. But you'll notice that the accuracy at 1 will start around 0.02, increase not quite 0.05, but the accuracy at 5, significantly larger, accuracy at 10, significantly larger, accuracy at 100, significantly larger. And you can know that your model is in fact converging because these values down here are going down for your loss and the F objective, which also includes the regularization. If those are going down, and then these values, the accuracies should be going up. If they're not going up, that means somehow your computation of the accuracy code has a problem with it. Are there any questions about that? Okay, we have just a couple minutes left in class, so I'm briefly going to mention what the difference is between these two different data set options is. And so we already looked at the insides of this data set right here. I want to next look at the insides of this data set right here. And what that looks like is, so I'm going to open it up here, Congress tweets.json. Actually, I have a smaller version right here to look up. Here, it's still a JSON file, but now this dictionary has this new additional field in it called features. And features is that vector that's output from the transformers model. So here I used one of my GPUs that I have available to automatically calculate these features and then just save them. And so the expensive part is done. Now it's just computing a linear model off of this. And so if you load this data set instead, it won't have to calculate those features for you. And so you can see right now, I don't know, we've let this run half of the lecture. Takes a long time, like 2 seconds per iteration. End that. But if we change this to instead use the this data set right here, and again, so in here I have a folder data features and just a single JSON file in there. If I delete that JSON file, I want data path pointing to the folder that contains the data. Hit enter. It'll take a little bit to start up. Oops, and let me just change one of these hyperparameters so that it'll we're able to run it. We'll see that it goes tremendously fast. After it's finished loading. So, well, I apologize for that. It worked for me before lecture. I must have changed something while during lecture that broke it somewhere. Looks like there's a dimension mismatch going on. So I will fix that and upload it back to GitHub. But yeah, that's the end of lecture today. I'll have this fixed by Wednesday. Happy to stick around and answer any questions that people have. Otherwise, I will see you all on Wednesday.
Professor, I had a quick question about the accuracy at K. Where do we put in that parameter for the code? Like, where in the code does that appear again?
So if you go back to the, let me share my screen again. The very bottom of the, right down here, this is where you add the code. And it'll look like, I think it took me like maybe 10 lines or so to actually calculate the accuracy at K for the 4 different K values. And then I called the writer.addScaler to add those values into TensorBoard. So it's like 15 or so lines that get added right here. That answer the question, Sabrina?
Yeah. I'm gonna have to digest that a little bit and I'll get back to you.
Okay. Maybe another thing that's important is K is not something that gets passed in anywhere. Specify what the K values you should be calculating for are right here. And so you'll, the way I have it done is basically a function that takes parameter K as input, and I call that function, and it, with K equals 1 or K equals 5 or K equals 10, and that function calls the, calculates it and writes it to TensorBoard.
Right, okay.